Okay, we're going to begin the module on linear, nonlinear, and mixed effects models. Today's lectures are going to be about simple linear models, and our first lecture is on general linear models. No readings for class, but there are some really great books here that, especially if you're newer to R, they have a great introduction to all sorts of statistics, go through everything very carefully, and they're real mathematicians, so they're very good at this. And they all have code to help you go through it as well in R. So these are really great resources. And Ben Volker's book is actually, there's also an e-version, which I have linked here, so would highly recommend. So when we're looking at our pipeline, you can see this is created for Tidy because Tidyverse, because the model section is very small, and so we're going to really be expanding on this. But today it does work out that we're just looking at linear models. And so the data we're going to be looking at today is a data set examining salmon residence time in streams and how that varies with sex, age, year, and precipitation. And this data set has multiple types of X variables, both categorical and continuous, and a single Y variable, which is residence time. So we can look at different types of linear models with the same data set. And so here's just a look at what the data look like. And so we're going to be talking about general linear models today. And general linear models refer to linear regression models that have a continuous dependent variable y, just a single one, and a single or series of independent variables x's that can either be continuous or categorical, and they all assume normal distributions. And these models can have specific names depending on their type, but they are all linear models. And I should say that these all assume normal distributions as opposed to generalized linear models that don't, and we're going to talk about those in the future. But to talk about the types of linear models we're going to talk about today, so there's regressions, and those have a continuous y and one continuous x, and you can use the function lm for that. There's ANOVAs, or analysis of variance, and that's a continuous y and a categorical x, and you can use either AOV or LM here. There are multiple linear regressions that have a continuous y but multiple continuous x's, and an analysis of covariance, or an ANCOVA, that has one continuous y and at least one continuous x and at least one categorical x, so all of the things. And so here are some of the assumptions. Here are the assumptions of general linear models. For the regression parts of these types of these linear models, that the relationships are linear or all linear, depending if there's more than one. A big assumption is that there are normal or multivariate normal distributions of the error variance, which is your epsilon, that there's equal variance among your groups or any of your variables, and that's homoscedasticity, and ANOVAs are pretty robust to this, just as a heads up. And that also that there's independence of your observed samples. So your data, the observations that you make, should be no correlation between them, that each individual is independent. And so the normality assumption, this is something that trips people up a lot. People get really concerned about this. So first remember, it's only with your y variable, not your x variable, so your dependent variable. So here we're looking at residence time. And the best way to tell if your data and hence your errors are normally distributed is to plot it. So we learned how to plot distributions of our data using histograms. So you try that. This data looks pretty normal. I will say that, with the sample sizes that we often have, which isn't really huge, these distributions they look normal-ish. That's mostly okay. Especially these general linear models, are really robust in many ways. But if you want to test to see if your data are normal, you can try a QQ plot. Again, the code for this is under the hood, so just check the markdown file on Canvas. But what you're looking for here are that your points are that fall along that predicted line. And so here we do pretty well. You can see at the top right-hand part of the graph, maybe they're off a little bit. And so this is just a visualization. This isn't a test. So if you wanted to actually test for this to see if your data are normal, you can do a Shapiro-Wilks test. And this has the null hypothesis that data are not different from a normal distribution, and the alternative hypothesis that they are different from a normal distribution. And so here's the code, and what you can see is that our p-value here for residence time is not significant, and that means the data are not different from a normal distribution. So that's good. We can move on with our data. We don't need to transform it. So let's talk about our first type of linear model that we're going to talk about today, regressions. Again, that's a dependent variable y that's continuous and an independent variable x that's continuous. So here is our equation where yi are the data, beta 0 is the intercept, beta 1 is the slope coefficient, and x, of course, is your data, and then epsilon is your error. And we're testing the null hypothesis that there's no relationship between x and y. So, okay, what does that look like in terms of questions? Here are a few samples. How does elevation x alter a plant's seed production y? So again, continuous x and continuous y. How does temperature alter a lizard's metabolic rate? How does the year influence the average global temperature? Those are all examples of regression models where you'd want to use data where you'd want to use a regression. And so does residence time within a stream depend on the amount of precipitation? That's the question we're going to ask with our data, two continuous variables. And the first thing to do is to plot your data just to look at it. And so here you can see we have two continuous variables, and this is what the data look like. And there could be a trend. We're not sure. We'll have to test it. And here is the code, is residence time a function of precipitation. And the result is that, so you run your linear model and then you do a summary of that model. That's how you get your result. And the result is that precipitation is significant where p equals 0.03. So yes, precipitation has an effect on residence time. And I want to point out that we had our regression equation, right? yi equals beta 0 plus beta 1 x plus epsilon. And you can actually parameterize that model from the estimates you get from your linear model result. So when you look at the estimate, the intercept, that 4.6 is actually your beta 0, and your estimate for precipitation is 0.097. And so you can plug those into your beta 0s and your beta i's, and that will allow you to actually parameterize that slope equation. Okay, and so speaking of residuals, so residual plots show the difference between your observed data y and your expected or fitted value y hat. So residual is y minus y expected. And if you want to plot your residuals, you can again see the code under the hood where you're just plotting that residual value for each individual observation. That's what the x value is here on this, or sorry, yeah, the x-axis is on this graph. You don't want to see a trend in your residuals. And if you see a trend when you're just looking across individuals, could be concerning. So it's nice to be able to plot your residuals and show, yep, no trend. But you can also plot your residuals with your actual x and y variables, looking at the actual slope. So here you have your expected mean line, the trend line. That's that beta 0 equals beta 1 x plus epsilon. And so here's your slope, and then here your x-axis is precipitation and your y-axis is residence time. So it's a bit different than before where you didn't have the x-axis was just the individual observation or the row. And so here you can see, as you look across precipitation, you can see where your residuals fall above or below the expected line. And so again, look under the hood for the code for this if you want to make this plot. Okay, so ANOVAs are next, and these models have a dependent variable y that's continuous and an independent variable x that's categorical. Here's your equation. Mu is the grand mean and alpha is the group mean. And so groups basically fall within categories. So within one category, say habitat type, you could have different groups such as forest, grasslands, and wetlands, for example. And so your null hypothesis here is that there are no differences among your groups. And so you're going to be testing to find out if there are. And here are some questions that you could potentially ask. How does a diet treatment alter an animal's growth rate? So again, your X here is categorical because you could have diets X, Y, and Z affecting an animal's growth rate that's continuous. How do nutrient additions alter plant species diversity? So nutrients, again, are categorical because it could be nitrogen addition, phosphorus addition, potassium addition, etc. How does the sex of an organism alter its feeding behavior? Again, sex is categorical. And how does plant family alter the plant's specific leaf area? And family, again, is categorical. And I want to just point out quickly that ANOVAs and t-tests are actually the same when you have two groups of equal size. So if your category just has two groups, male or female, then an ANOVA and a t-test are going to give you the same result if you just have one X variable. So here's just a little toy data set, and you can see that if you run a t-test or an ANOVA, so we're going to run AOV in the future, but you can do LM and then ANOVA around that. You get the same result. Okay, so with our data, we're going to ask the question, is residence time within a stream a function of the age of the fish? So here we have adult fish, juvenile fish, and moderate aged fish. And you can see that, again, potentially looks like there's a difference in the distributions of this data with residence time, but we'll have to test to find out. And so here is the code, is residence time a function of age? And then we do a summary of that model output. And here you can see that, yes, age significantly predicts residence time. But as you can see, this model is only saying age is affecting residence time, but we know there are 3 ages, and we don't know which ages are actually different from each other. And as we saw in the graph, right, there could be differences among adults, juveniles, and moderate aged fish, but this model doesn't tell us that. The ANOVA just tells us, is age significantly affecting residence time? And so if you want to test for differences among groups, you have to do a post hoc test. And this allows you to know which groups are different from each other. So we're going to do Tukey test, Tukey HSD, and here that does all comparisons. And here you can see that juveniles and adults are significantly different from each other. And so are moderate-aged individuals and adults. But moderate-aged and juveniles are not different from each other based on that p-value column. Okay, so moving on to our next type of linear model, multiple linear regression. Here you have a dependent variable y that's continuous and multiple continuous independent variables x, and they're all continuous. So here's our equation for that. And beta i's are the, so 1, 2, 3, etc., are the partial regression coefficients. And that's the effect of xi while holding all other x's constant. So we're going to be looking at one of our continuous variables while holding all the rest of them constant. So that's how these models work. The null hypothesis is that there are no differences among slopes. And here are some questions that you might ask. So how does elevation and temperature alter plant seed production? So again, elevation and temperature are both continuous. How does temperature and humidity alter a lizard's metabolic rate? And how does the year and atmospheric CO2 levels influence the average global temperature? So again, let's try to plot our data because I think that's always the best way to do this before you actually run the tests. And here you can see we've plotted, our question is, right, that we're going to ask with our data is, does residence time within a stream depend on the amount of precipitation in the year, two continuous variables? So we've plotted precipitation by residence time and then colored the points by year and drawn the lines, the trend lines through the points. And you can see 2 years look very similar and 1 year looks like it might be different, 2001. However, the confidence intervals of those lines are very big, so it's pretty hard to tell just from looking at the data if we're going to find a significant effective year. So we'll have to test. And here is our test to look at if residence time is a function of year and precipitation. And here we find that only precipitation is influencing residence time, year is not. So precipitation affects residence time while holding year constant, but year does not affect residence time while holding precipitation constant. Okay, moving on to our last type of model that we're going to talk about today. ANCOVAs, or analysis of covariance. And here you have your dependent variable y that's continuous again, but you're going to have multiple independent variables x, where at least one is continuous and at least one is categorical. And your equations start to get kind of complicated, so really don't worry about it too much, but just know that we're testing for the null hypothesis that there are no differences among slopes or no differences among groups. And what these models do is first compare the slopes and then compare the groups while holding the effects of covariance constant. So here are some questions that you might ask, some examples of questions that might require an ANCOVA. How does elevation and nutrient addition alter a plant's seed production? So elevation is continuous, nutrient addition is categorical because nitrogen, phosphorus, etc. How does the temperature and sex of an individual alter a lizard's metabolic rate? Or it can start to get really complicated, like how does the year and atmospheric CO2 levels and the habitat type influence plant biomass? So here you can have year and CO2 levels, those are both continuous, and habitat type is categorical, like grasslands, wetlands, etc. And so you can see these can get pretty complicated, but are really nice models. And so with our data, we're going to ask, does residence time within a stream depend on the amount of precipitation, the year, and the sex of the fish? So again, here is residence time a function of precipitation, year, and sex. And when we run this ANCOVA, what we see is that precipitation and sex are significant predictors of residence time, but year is not. And so, again, as these models get more complicated, you start to elucidate different trends. And so what does that data look like? I specifically saved this to the end instead of plotting it first because it was getting pretty complicated. And here we only had two significant factors, so that's what I'm going to plot here. So this is a graph of your two continuous variables, precipitation time and residence time. And then I colored the points by the categorical factor that was significant. And so here you can really see the results in graphical form. So there is a positive relationship between precipitation and residence time, and the genders also have significant relationships, that males always have longer residence time than females across all precipitation types. And so that's it for our section on linear models. So please complete quiz Canvas 4.1 on Canvas and continue on to the next lecture.